Hi, so in this video we are going to be doing double integrals. So before we get started, let's first understand what that is. So here are my notes, and notice I wrote iterated integrals, and essentially they mean very similar things. Integrated integrals mean we're sort of breaking down the double integral, and double integral is the actual more general term that we use. So first of all, let's understand the idea of integrals. So back to one variable calculus. In one variable calculus, we have a graph, whatever, and then to find an integral, a definite integral, we have like points A to B, for example. Then from here, it will be 0 to B, for example. And in one variable calculus, we learned that the integral of a curve means an area under the curve. And so for double, then what would that mean? So first of all, we will first define R, which is basically a rectangle. So this is the graph here, defined by the interval from A to B in the x-axis and C to D from the y-axis. And we let that f to r squared, basically meaning that the curve is continuous, and we want to consider that we call I of x as just a function. And remember, if we were to find integrals, it means area under the curve. So a double integral would mean that basically it would be the area inside whatever we have enclosed by these domains, basically. Because here, unlike one variable calculus where we only have, like when you think of an integral, a definite integral from A to B, the bounds are usually defined by the x-axis, but now we also have the y-axis. So to define that, we have two different forms. We have the integral of the graph fxy in multivariable calculus from C to D, which is in terms of y, so we are integrating with respect to dy. When I say with respect, you should be already familiar with that term because, for example, if you did partial derivatives, you learn how to derive with respect to x or with respect to y, basically ignoring the other variable as a constant. So when we do this, this would be with respect to y. So basically back to the idea of single variable. And then on the other hand, we have the integral from A to B. So if we want the integral from A to B based on the interval from the y-axis, then essentially what we're trying to do is combine two of them together. So here is I of x, which is what we defined here, and then now we want to enclose it with respect to x-axis, so we put the dx outside. So basically it's a layer. On the other hand, it could be the opposite. We could first integrate with respect to x and then with respect to y. So the same idea still is the same. So now, I know this is kind of confusing, so now let's actually try to do the problems. The main goal to doing these problems is to know how to integrate with respect to dy or dx. So if we take a look at this first problem, one strategy to do is we first focus on the integral inside, and then we go outside. So first, inside we have the integral from -2 to 4 of x over y dx. So first off, when you look at this problem, it seems a bit scary because there's both x and y. So how do we actually integrate? Because in one variable calculus, we only learn how to integrate with only one variable, which is usually x. And so now that we have the y, what do? So first off, we want to notice that in this specific integral, we see that it is dx here, meaning it is with respect to x. So that means we are treating y as a constant. So like, let's say a simple problem, if I were to derive x, I keep mixing the terms. If I were to integrate x, and let's say I have a number in front, like 1 over 4, for example, we learned that the basic integral to do that is just x squared over 2, and the constant stays there, right? And so this is the idea that you should be already familiar with how to integrate basic functions. But now we just have a y, and we want to treat y as a constant. So if we treat y as a constant, we can essentially ignore it for now and only focus on x. The integral of x would be essentially x squared over 2, right? And then we have the y that's just there. And that's it. And then you got to plug in the boundaries, which is 4 and -2. And if we plug that in, we get 1 over y. Remember that we are integrating with respect to x, so that means these bounds would be plugged into x, and y would just remain as y. So if I were to do that, then we have x, which is 4 squared over 2, minus 1 over y times -2 squared over 2. So if I were to simplify this, this would be 16 minus 4 over 2y. And if we were to simplify this even further, we get 12 over 2y, which is also the same as 6 over y. So now that we have that, we have our first part that is already done. Now the second part, we just need to plug this in. So this is the second part. Now we only focus on integrating with respect to y. So we have 1 and 3, and the inside function, or the inside integral, we already solved it to be 6 over y. So all we need to do is just put it back in, and this time it is with respect to y. So this should be pretty simple. You have already learned this. The 6 would be a constant, so we can just leave that outside. 1 to 3 of 1 over y dy. And note that it is 1 over y, which is the typical ln function. So then this would be ln of y from 1 to 3, which is going to be ln of 3 minus ln of 1. And ln of 3 is just ln of 3 if we don't use a calculator. Ln of 1 would be 0, so we have our answer just 6 ln of 3. So there you have it. The way to approach this problem is to do it step by step. And so that's how you do it. First focus on the inside integral and then the outside. Now let's apply the same idea to a different problem. This time we're trying to integrate with respect to y first. So first we have the dy. So let's try that. If I were to do this integral, I would want to first focus on the inside integral first. So we have e to the power of 3x minus y dy. To solve for that, we are integrating with respect to y. So that means 3x is a constant. So essentially, if we think about anything, e to the power of any number, or e to the power of -y, basically, it's just going to be e to the power of whatever is inside, and then the -y goes to the outside. So we have -1 over 1, which is just -e. So if it's easier to understand, you can also use u sub. So we could do u equals to 3x minus y, and we do du over dx with respect to y would just be -1, because remember, x is a number or a constant, so we don't care about that. And if we isolate, this is my bad. It should be du by dy with respect to y. So it would just be -1. So dy would then be equal to -du. So if we were to do that, it's still we'll still end up getting the same answer. We have e to the power of u negative, and we have du because we're plugging dy in. So the dy becomes a -du, which is here. So if we do that, and if we plug back in the u, which is 3x minus y, we get the same thing as what we got earlier, so same thing. Anyway, now we can try plugging in the values. So we have -e 3x, remember it's with respect to y, so we only care about y, so negative 4 minus e to the power of 3x minus 2, which is basically negative e 3x minus 4 plus e 3x minus 2. And now the second step is to plug this into here. So we have the integral from 1 to 2 of negative e 3x minus 4 plus e 3x minus 2 dx this time. So if we derive with respect to dx, we can do what we did earlier, so let's try that. You don't have to, but I think it's a bit easier to understand if we do u sub. So if we were to do u sub, first off we want to separate the integral into two parts, so it could be done like this. You should end up getting the same answer. So for the first part, we let u equals to 3x minus 4 du over dx this time, right, is with respect to dx. We get 3 only. The y, oh wait, sorry, I mean the 4, it's just a number, so it's 3. And if we isolate dx, we get 1 over 3 du. So if we were to do this, this would be, this would be negative eu of 1/3 du, which is basically the same as negative 1 over 3 1 to 2 eu du, which is the same as e to the power of u. And we want to plug the u back in, so e to the power of 3x minus 4 from 1 to 2, we get negative 1/3 e to the power of 3 times 2, which is 6. 6 minus 4 is 2, minus 1/3 times e to the power of 1. X plugged into 1, 1 plugged into x, so 3 minus 4, which is negative 1. So we get that plus 1/3 e. So that's the first part. The second part, we let u equals to 3x minus 2. Du by dx would be 3. So dx is 1/3 du. So if we were to do this, we have 1 to 2 of e to the power of u times 1/3 du. And we put the 1/3 outside to make life easier. And eu, the integral is just eu, and plug that back in. So e of 3x minus 2, 1 to 2, and we get 1/3 e to the power of 3 times 2 is 6, so it's 4, minus 1/3 e to the power of 3 minus 2, which is just e. So there you have it. Now we combine everything, so we get this plus 1/3 e, 4 minus 1/3 e. So there you have it. If you want to make it even simpler, you can simplify that or factor out the 1/3. So we get negative e squared plus 1 over e plus e to the power of 4 and minus e. So there you have it. That is how you do these kinds of problems. Takeaway would be to, when you do double integral, be very careful with what you're integrating with respect to. It's important that you look inside the function, whether it's dy or dx. If you see dy, it means to integrate with respect to y, and if you see dx, you're integrating with respect to x. And one main idea is, let's say if I were to do these problems again, but switch the order, so instead of dy, I do dx, and here it's dy. potentially I would get the same answer, given that it is continuous. And same thing goes for here. And when it comes to deciding, I think maybe in the future videos that I'll be doing, maybe I'll be discussing when you can switch to like dy first and then dx, for example, because ultimately you'll get the same answer, but sometimes it depends because you want to integrate what is most easiest. So if you did the other order, there are some problems that would make life harder. So ultimately we want to integrate it in a way that is easiest. Thus, it depends where you put dx and dy, but ultimately if you flip those, the idea is that it will be the same according to our definition of iterated integrals here. So that's it for today's video on double integrals. I hope you guys enjoyed it, and thank you for watching.